Hi, I'm Mike Rowan, and this is part 4 of the Retro Tinker Game Master Cartridge, Understanding Bank Switched ROM. So far in this series, we've focused on the SN76489 sound chip. Now we're going to move on to the other very important feature of the Game Master Cartridge, the onboard ROM socket and the built-in bank switching feature. A ROM is a read-only memory. When we use the term ROM, we're generally referring to two types of devices. The actual chip can be a PROM, a programmable read-only memory, or an EPROM, an erasable programmable read-only memory. The main thing to remember is that the ROM is where you store your program on a cartridge. The Game Master cartridge has a 28-pin socket for your ROM. Here are a few popular EPROMs that you can use in the Game Master cartridge. We're going to use the 64K 27512 EPROM for most of the examples. The 64K EPROM has 16 address lines, A0 through A15. Likewise, there are 8 data lines, D0 through D7. Each byte of data stored on the EPROM is accessed using a unique 16-bit address. In other words, there are 64K, or 65,536 possible addresses, and at each address, 1 byte of data is stored and made available on pins D0 through D7. So the range of addresses possible with 16 address lines is from the lowest, with all address lines set to zeros, to the highest, with all the address lines set to ones. This provides 65,536 addresses. That's 0 through 65535. So 64K equals 65,536 bits. So we have a ROM chip that can be addressed by the color computer. When the Game Master cartridge is plugged into the color computer's cartridge port, the address lines and data lines get connected together. This is how the color computer can communicate with the Game Master cartridge and how it can read and access the ROM. But the color computer's memory map only allows for a little less than 16K of address space to access the cartridge ROM. Here is part of the color computer memory map from the Technical Reference Manual. This is for the COCO 1 and 2, but the COCO 3 uses the same start address for compatibility. The cartridge ROM area begins at address C000, and on the COCO 1 and 2 it ends at FF00. So the address range for the cartridge ROM is C00 through FEFF. If you do the math, you'll see that this range actually is a little bit short of 16K. It's only 16,127. The COCO 3 actually uses addresses in the FEXX range for other purposes. So if you want your ROM to work on all COCOs, COCO 1, 2, and 3, the top address that you can use for the ROM is FDFF. So the number of bytes we can read from a ROM becomes even smaller, 15,871 bytes. Let's say we have a 16K ROM chip we want to access from a COCO. A 16K ROM would only have 16,384 addresses, 0 through 16383, or 3FFF in hex. But the color computer memory map dictates that the first cartridge ROM address begins at C000. So how do we get the COCO's address C000 to read the address at 000 on the ROM? In reality, a 16K ROM only has 14 address lines, because that's all that's required to address 16K. So there are 2 address lines that are not even connected to the ROM because there are no pins on the ROM to connect them to. The clever effect of this is that address C000 on the color computer accesses address 0 on the ROM. You could, of course, use a 32K or 64K ROM, but the color computer can only access the first 16K of any ROM anyway. But through some clever circuitry aboard the Game Master cartridge, we can divide a larger ROM into multiple 16K banks, and then switch to which of the 16K blocks the color computer can read from. So we can have a 64K ROM that can be divided into 4 16K blocks. Since the color computer only needs 14 address lines for 16K, only the lower 14 address lines are connected to the Game Master cartridge. However, a 64K ROM does have 16 address lines. We can use these 2 bits from the Game Master cartridge to select different blocks of 16K to present to the color computer. Let's build a memory map for the 64K ROM so that you can see the effect of the 2 highest address lines. The lower 14 address lines are shown in black here. They represent the 16K address space that would be connected to the color computer. In other words, those are the lines that are actually connected to the color computer from the ROM. The bits in red are the 2 bits that we'll use to switch 16K banks. So the first block begins at address 0, and it ends 16K later at 16,383, or 3FFF in hex. You can see the first 14 address bits are all 1s at the top of the 16K block. So if we look at it from the 14 address lines, we're going from all 0s to all 1s, and that's the entire range of 16K. In the second block, we will start at 16,384, or hex 4000. Now you can see that what has happened is that the 2 highest bits are now set to 0, 1. And you can start to see a pattern that's the same as the block number that we're talking about. So block number 0, those high bits were set to 0, 0. For block 1, they're set to 0, 1. And from the ROM's perspective, we're now at address 16,384. And the top of that block will be 32,767, or 7FFF in hex. And again, you can see that in the 14 bits, you can see that the range goes from 0, all 0s, to all 1s, and another 16K block. And it's the same for the next block. That block goes from 32,768 up to 49,151. Again, you can see that the high order bits are set to the block number. This time it's 1, 0, or in binary, that's 2, so that's block 2. And then finally we have block 3 that goes from 49,152 all the way up to 65535. And you can see that the highest address lines are set to 1, 1, which would be 3 in binary. And that equates to block 3. So let's look at the start address for the first 16K in the 64K ROM. That's address 0. And if we look at the color computer bus, the lower 14 address lines are connected, and the 16K is available via these 14 lines, but we're actually looking at the first block or bank 00, on the 16K ROM. Now if we change the ROM address to the next 16K block, on the color computer address, the lower 14 address lines are connected, and 16K is available via these 14 lines, but we're actually looking at the second block, or bank number 1, 01, on the 64K ROM. If we change the ROM address to the third 16K block, on the color computer bus, the lower 14 address lines are connected, and 16K is available via these 14 lines, but we're actually looking at the third block, or bank 10, that's 2 in binary, on the 64K ROM. And finally, if we change the ROM address to the fourth 16K block, on the color computer address bus, the lower 14 address lines are connected, and 16K is available on those 14 lines, but we're actually looking at the fourth block, or bank 11, 3 in binary, on the 64K ROM. So we can see that the highest 2 address lines control which bank of 16K we're accessing. But how do we control this 2-bit value from the color computer, especially since these address lines aren't even connected to the color computer? There's an addressable register aboard the Game Master cartridge that's wired to the 2 highest address lines of the 64K ROM. This register can be written to at address FF40. Simply send a byte to address FF40 to set the register to either 0, 1, 2, or 3. Note that this register is write only. You can't read what value is in there. In the example shown here, the register is set to 3, 1, 1 in binary. If we want to change to bank 0, then from BASIC, issue the command poke and H FF40, 0. This will write 00 to the bank register on the Game Master Cartridge, and it will change to be bank 0. If we want to change to bank 1, then from BASIC, issue the command poke and H FF40, 1, and this will write 01 to the bank register on the Game Master Cartridge and change our block to block number 1. If we want to change to bank 2, you know where this is going. We're going to poke and H FF40, 2, and this will write 10 to the bank register on the Game Master Cartridge and switch us to bank number 2. If we want to change to bank 3 again, then from BASIC we do a poke and H FF40, 3, and this will write 11 to the bank register on the Game Master Cartridge. So what good are these 16K blocks of memory? Well, potentially it means that you can have programs larger than 16K on a ROM pack. You can have additional space for data on a ROM pack. Your code could be written to load from bank 0 and then switch to another bank to continue loading. You could put music data, digitized sounds, or level data. You could have more than one game in ROM, and you could have a start menu that allowed you to choose which game to play. You name it, you're really only limited by your imagination. Well, this ends part 4 of the Game Master Cartridge series. You can see that it offers a great deal of flexibility in developing color computer ROM packs. The sound chip produces great sound quality without overburdening the programmer or the color computer. The ROM bank switching capability enables you to deliver programs larger than 16K on a cartridge. And as added bonuses, the parts are low cost and they're period correct. Now I plan to continue the Game Master Cartridge series with additional code examples. And until next time, thanks for watching and long live Coco.